The question that I have is, could you derive Terzaghi's 1D consolidation differential equation? So let's discuss Terzaghi's one-dimensional consolidation theory. I'll try to be as brief as possible, but I think the derivation of the governing differential equation is kind of important, so I'm going to spend a little bit of time on that. We'll derive the equation with respect to this field setup right here. Basically, I have a horizontal deposit of soil with a clay layer sandwiched between two sand layers, and the profile is subjected to a uniform vertical pressure equals delta sigma z. The water table is right here. So if I were to insert some tubes like this, the water will rise to this level, to the level of the water table, before we apply the surface pressure, right? When we apply the surface pressure, since water takes all that load initially, the pore pressure is supposed to increase instantaneously. The increase is supposed to be exactly equal to this, the surface pressure at all of the points. So how does it show up in the tubes? Well, the water level will shoot up to this level where this height right here is delta sigma z divided by gamma w. But the clay cannot hold that pressure on these boundaries because we have a sand layer here and the sand layer here, right? So the sand layers are much more permeable than clay layer. So the pore pressure would immediately dissipate back to the initial hydrostatic pressure on these boundaries. These are what we call the drainage boundaries. When we have two drainage boundaries surrounding the clay layer, we call this the doubly drained problem. If you have only one of them, then we call it a singly drained problem. In fact, these will become our boundary conditions later on to solve the differential equation. While the pore pressure remains zero here on the boundaries, it's not going to be zero inside the clay layer. So this distribution of pore pressure inside the clay layer will create a hydraulic gradient in these directions. So the water is going to start flowing. As the water flows, pore pressure is going to dissipate, and you will see the levels of the water in the tubes will start dropping. Okay? So at various times, if you were to connect the levels, it'll look something like this at various times. So we start from t equals 0 here, right? And then at various times it's going to keep dropping, and eventually the pore water pressure change will dissipate everywhere within the clay layer, and the water levels will drop completely back to the initial hydrostatic level. So we'll refer to this change in pore water pressure as the excess pore water pressure. So the excess pore water pressure is both a function of time and depth. So we'll just measure the vertical coordinate from the top of the clay layer here, and we will call the excess pore water pressure as U as a function of Z and T. So the objective here is to obtain a mathematical solution for the excess pore water pressure. It turns out once you do that, you have solved the consolidation problem. You can calculate everything else based on that. So this is what Terzaghi had done, and this has come to be known as Terzaghi's one-dimensional consolidation theory. So to start the process, we'll just take this little differential element, turn the axis around, and draw the differential element over here and mark important variables on that. Let's just say the velocity of water flow on this face is Bz, and then on this face is going to be Vz plus dVz by dz times dz by calculus, right? So a certain amount of water goes in, certain amount of water comes out. And if you recall, in the two-dimensional steady state seepage analysis, we equated the two. Q in was equal to Q out, right? And that's not going to be the case here. Here we are going to consider the change in volume as this process takes place. Why would the volume change? Well, as the applied pressure is gradually transferred from water to the soil grains, right, the effective stress increases. As the effective stress increases, the weight ratio decreases. All right, that's why the volume changes. So here is our modified equation. Q in minus Q out equals rate of change of volume. Denoting the volume by V, here is our equation. So here dV over dt is the rate of change of volume. We're going to relate this to the rate of change of weight ratio as shown here. To do this, once again, we invoke the proportionality rule that we used before. Here's your phase diagram. Here is the differential element, right? So we find the equivalence between the two. So you go through this analysis and you find that the rate of change of volume is then given by this equation where on the right side we have 1 over 1 plus E naught multiplied by dE over dt times dx times dy. So at this point we just call this equation number 2. The next step is to relate the rate of change of weight ratio to the rate of change of effective stress. So to do that, we utilize this relationship right here. And from that relationship, by rearranging it, we have this delta E equals minus A sub B times delta V prime, delta sigma V prime. So you differentiate both sides with respect to time, we get this relationship. So we'll call this equation number 3. The next step is to relate the rate of change of the effective vertical stress to the rate of change of the excess per water pressure. To do that, we go back and consider point A one more time. The current vertical effective stress at that point equals the vertical effective stress that existed before the application of the load plus a change. Where did the change come from? Well, every time the excess per water pressure dissipates, the vertical effective stress at that point increases. And therefore, the change in the vertical effective stress at that point at any given time equals delta sigma z minus uz, where uz is the excess per water pressure at point A, right? We substitute this back in this equation, we have this equation. And we recognize that these two quantities are independent of time. And therefore, if I differentiate the vertical effective stress with time, we get this equation. Our final step before we assemble everything is to bring in the Darcy's law. To do that, we need the hydraulic gradient. So let's look at point A one more time and write down an equation for the total hydraulic head. The total head consists of the elevation head plus the pressure head, right? So the pressure has two components, the initial per water pressure and the excess per water pressure. If we group this term with the first of the two terms in the pressure term, we recognize that this is the total head before the surface pressure was applied, right? And that shouldn't have changed from point to point. In other words, there was no water flow before we applied the surface pressure. So this should be independent of the depth. And therefore the hydraulic gradient, which is dH over dz, is given by this equation right here. So now we can apply the Darcy's law. Velocity of water flow in the z direction equals permeability multiplied by the hydraulic gradient. And we have to introduce a negative sign here. And if you recall, we did this once before. Basically, if the head increases this way, the water flow is going to take place in the opposite direction. I'm going to differentiate this equation one more time with z so that we get dvz over dz. I rewrote these two equations from the previous slide. Well, now you assemble these equations as follows. For dv over dz in equation number 1, you put this. And for dv over dt, you put this. But for dE over dt, you're going to use this. But for d sigma v prime over dt, you substitute this. All right? So eventually, everything will be in terms of the excess water pressure. So I left the subscript z that I had over here. All right? So this is the final differential equation governing the consolidation in one-dimensional situation. And this is what is called the Terzaghi's one-dimensional consolidation equation. And we have a parameter here, and this is called the coefficient of consolidation. Coefficient of consolidation equals permeability divided by the coefficient of volume change multiplied by the density of water. In obtaining the solution to this differential equation, Terzaghi assumed that the coefficient of consolidation remains a constant, which is a reasonable assumption, although it's not strictly true, because the permeability is going to change whenever the void ratio changes, the permeability changes, right? And similarly, the volume coefficient of volume change is also going to change because the effective stress keeps changing during the consolidation process. But usually what happens is, as the vertical effective stress increases, the soil becomes denser, permeability decreases, and the coefficient of volume change also decreases. So both of these decrease, and therefore C sub V remains approximately a constant. So this is the famous Terzaghi's one-dimensional consolidation equation. And you can see we had to put together a number of different fundamental concepts to arrive at this. So the derivation is admittedly a little complicated. I'm not going to cover this in any of our tests or quizzes or anything like that. If you are like me, you want to know where everything comes from, right? So this is to satisfy your curiosity. But everything I do from this point on is important. We're going to be talking about the solutions to this differential equation, and we are also going to be talking about how to apply the solutions to solve some practical consolidation-related settlement calculations. One final thought before we leave this slide is that it's amazing, if you really think about it, that Terzaghi was able to come up with this almost a century ago. And we are still using his theory in real world settlement calculations.